Well, pre-calculus classes, as always, good morning, good afternoon, or good evening. We are going to start into section 3.4 here. This is one that does have two parts to it, so we won't get through everything in this set of notes here, but we are going to start solving some exponential equations in 3.4. The second half of the sections where we'll solve logarithmic equations. So, as we do get started in 3.4, though, there are a couple of things we're going to kind of go back and just remind you of from earlier, I think in maybe 3.1 or 3.2, when we talked about some general properties. Now, the one-to-one properties. If you have some base b to the x and that expression equals the same base b to the y power. Well, basically what the one-to-one property says is that as long as the bases are the same, that means the exponents will form an equality, an equation. So, same thing works with logarithms. If you have log base b of x and it's equal to log base b of some other quantity y, those two quantities within the logarithms will equal each other as well. Those will be things that, we use a fair amount in this next section. And then the inverse properties. I know we've already talked about it, that exponential functions and logarithmic functions are inverses of each other. If you have a base and then you take it to an exponential expression with a logarithm of the same base, the base and the logarithm cancel, leaving just an x. You see this a lot, especially when we work with e and natural log. And especially this second part, log base b of b to the x. Again, here's where you move the x out front, and then those are just equal to 1. But either way, those do both equal x. Now, as far as solving, a variety of exponential equations. Now, the one thing notice, round to 3 decimal places. So, if we have e to the x equals 70, well, we are solving for x. We need to get rid of e. The only thing that we can use to get rid of e, the exponential base, is natural log. Now, we're going to take the natural log of each side. What we can then do with this exponent is move it out to the front, and then natural log and e cancel. So x equals the natural log of 70, which 4.248. So, fairly simple one there. I'm going to go ahead and actually work down the column here, simply because these two problems really work well together. If you have e to the x minus 4 equals 60, well, first thing, we are going to add the 4 over. And I suppose if you want, I can even show that, just like the one we did up here. E to the x equals 64, and those cancel, allows me to move the x out to the front, and I do want to show it's balanced. So x equals natural log 64, which is going to be a little bit smaller than what we just had there, 4.159. So, there are a couple of those. Now, these next two are going to be a little more involved because, unfortunately, our bases are not ones that we have logarithmic functions for. 6 times 2 to the x equals 42. First thing, you cannot multiply the 6 and the 2. I do need to go ahead and divide the 6 over. So 2 to the x equals 7. Now, here is where I know I mentioned with the change of base. The only time I actually use natural log is if I'm involving e. For this one, I don't have e. I'm just going to use regular log. Now, unfortunately, log and 2 don't cancel, but what that still allows us to do is move the x out front to where we can at least now get it by itself. And to do that, we divide by log 2. And so essentially what we're doing here is change a base. And so when I enter that in, log 7 divided by log 2, 2.807. All right, so this next example, I can already tell you that there is no way I'm going to be able to fit this in that small portion, so I'm just going to rewrite it before I work this out. All right, this one actually has a lot of steps involved here. So, main thing you do have to kind of watch for is just make sure you do them in the correct order. So first, add the 4. So 2, 3 to the 2t minus 5, and that's all a power. I didn't do a good job of showing that. Up here, divide the 2, 3 to the 2t minus 5 equals, because we're going to end up doing a lot all the way through, I'm going to go ahead and just make that a decimal now. All right. Again, you have a base with a variable exponent. We have to use a logarithm. Again, it's kind of up to you, either log, natural log, either way. I can move this out to the front. So 2t minus 5 times log 3 equals log 7.5. And then from here, again, kind of like our change of base, divide the log 3 over, and 2t minus 5 equals, I have absolutely no idea what decimal that is, 1.834. All right, so once you get here, you've done the vast majority of the algebraic work. Now just add the 5, so 6.834, divide the 2, 3.417, roughly. So like I said, this one has a lot of steps involved. Main thing you do have to really be careful is just make sure as you go through it, do not get any of those steps out of order. Otherwise, it'll completely change the answer you get. So that one definitely most involved thing that we'll probably look at here today. The next couple examples be a lot easier. Now, 2 to the 2t minus 6 equals 32. Now, like I said, solve without a calculator. There are going to be some things, you are certainly going to be asked to do without a calculator. And what that tells us is we can rewrite things as the same base. Well, 2 can't really be rewritten as anything else, so we're just going to leave it. Now, 32. 2 to the first is 2, 2 to the second is 4, 2 to the third is 8, 2 to the fourth is 16, 2 to the fifth is 32. So again, that one-to-one property says, hey, we can now set 2t minus 6 equal to 5, and then 2t equals 11, divide your 2, and t is 11 halves. So again, not too bad to do without your calculator. All right, for example B, 1/2 to the x plus 3 equals 16. This is one where I am actually going to go ahead and rewrite both of these. Now, 16, 2 to the fifth was 32, so 16 is 2 to the fourth. We can rewrite 1/2 as a power of 2 as well. It's 2 to the negative first. Now, when you do that, if you rewrite where there's already a quantity as an exponent, you just distribute. Negative x minus 3 equals 4. And so from there, we can add the 3 over, and then if negative x is 7, x is negative 7. So, again, those two, a lot easier than when we just did. All right, solving quadratic exponential equations. Well, if you have something like this, e to the 2x minus 3, e to the x plus 2, think of it as x squared minus 3x plus 2. This is essentially what we're factoring. What multiplies to 2 adds to negative 3, negative 2, and 1. So when I factor this, now, it's not going to be just x minus 2. It's going to be e to the x minus 2 and e to the x minus 1. So, e to the x times e to the x. Well, when you're multiplying, you add powers. X plus x is 2x. I have minus 2 e to the x minus 1 e to the x. That's where the minus 3 e to the x comes from. And then, of course, the negative 2 and the negative 1 is the easy part. So now, e to the x minus 2 equals 0. E to the x minus 1 equals 0. So e to the x equals 2. E to the x equals 1. Well, to get rid of e, natural log. Those cancel, and then we can move the x out to the front. I'm going to start with the easy one. The natural log of 1, if you don't remember the property, it's 0. Now the other one, natural log of 2, does not come out nice and neat. 0.693. I realize now we know where it said, hey, go ahead and go to any set decimal place, but everything else we've gone 3 places, so I'll stay consistent with that. So, solving quadratics, you can factor with e. Whether or not you did any of that last year in Algebra 2, I don't know. Good chance that's something that is entirely new. All right, one final question. Again, kind of like the one I did on example 1D. This one, unfortunately, is also going to require a little bit of space. So, 5 to the x minus 2 equals 4 to the 2x plus 3. Unfortunately here, we cannot, like either 2a or 2b, rewrite these as powers of other bases. So what we're going to do is take the log of each side, and then that still allows us to move our powers out to the front. So we have x minus 2 times log 5 equals 2x plus 3 times log 4. Now, from here, what we're going to have to do, because we have a variable here and here, I know we normally haven't done this, but we are going to distribute. All right, so x log 5 minus 2 log 5 equals 2x log 4 plus 3 log 4. So, to now work further, we need to combine like terms. Well, this is a variable expression. This is a variable expression. These are constant terms. So, I'm going to subtract this over and add this over. Now, we can't technically combine any of these, but what we can do, x log 5 minus 2x log 4 equals 3 log 4 plus 2 log 5. Well, x times log 5. I have no idea what log 5 is. 0.699. So this is 0.699x minus 2 times log 4. $1.204 x. And as much as anything, just so it's a lot less writing, 3 log 4 plus 2 log 5 is 3.204. All right, so now just take 0.699 minus 1.204. So it's like negative 0.505x equals 3.204. And then we can divide. And again, I have no idea what that is. Negative 6.345. So, again, a lot of button pushing on this question. But again, that is where you may end up using logarithms to solve. So, like I said, this is the first half of 3.4, solving exponential equations. In the second half, we'll solve logarithmic equations.